continue what we did last week. A few announcements. Homework 4 is, I announce it hereby. It will be available off the website to download. Ron, can you make sure it's on Canvas?
Yes.
So it will be on Canvas, and you have 2 weeks from today to submit it. Yeah? Sorry?
Are we still dropping the lowest homework?
Yeah, we're dropping the lowest homework, yeah. Which means you can drop 1. Then on the exam, I didn't completely make up my mind if I should do a take-home or in class. I know, I heard some students are stressed, but there is really no reason to be stressed. I don't know why is at home, take-home less stressful than in class. I don't understand the point of it. I mean, it sounds to me like in class, you do 2 hours, 3 hours, that's it, you're done with it. Is there a strong preference for take-home here? This is that I understand. Yeah? You prefer take-home? Why?
It's true, my stress costs more hours.
Okay, but is that a good thing for you? It's not clear to me this is good for you. So here's the thing. There is, when I give a take-home, usually I would give take-home. That's what I would do every year. The problem with that these days, you have the AI, and AI can, I'm pretty sure it can solve everything. And it's too much of a temptation not to look at the AI. Not that I don't trust you, I do trust you. 100% I trust all of you. But it's too much of a temptation, that's what it sounds to me like. No? And then if you have to learn for the exam, you take the exam class, I think you'll get more out of it. It might sound problematic, but it's not. Your grades are going to be fine. I guarantee. I should probably stop recording. Your grades are going to be the same grades as any other class. That's not going to be any difference to that. The question is, what do you take home with you? Do you take home with you some lame calls that, you know, oh, the instructor dumbed it down to us and so on like we're used to? Or, no, actually the instructor made sure that we learn and we, you know, insisted on high standards, insisted on exam. Then at the end of the day, I think you'll feel great about yourself. That's what I think that's what I would prefer. I'm still debating it, you know. I mean, I appreciate all of your opinions, but I'm still debating it to myself. Question?
Is it the same time that take home as in person?
Probably take home. It's going to be a bit more time and a bit more difficult question. It doesn't really matter, right? I mean, we're at the end of the day, I'm kind of comparing the different exams that I get. I think none of it matters. In my opinion, if you pay attention in class and you do your homework, you're probably prepared. You don't need to do anything, any other studying besides that. Yeah?
If it's in person, are we allowed to bring like notes?
You're allowed to do whatever you want. You have to sign the honor code, which means you don't use the AI on your phone. Besides that, do whatever you want. Yeah.
So we don't have to memorize it?
No memorization. Yeah. Yeah.
If you are going to change your mind, when do you think you could? I'm looking, and if like this is my only in-person exam. If this were to be online, I can be travel somewhere like end of the year.
So that is the only good reason I hear for making it take home, because then you're more flexible, right? So what I do is take home. You have like 2 weeks. Here, take it. You know, time yourself for whatever, how many hours, and return it back to me. It's flexible. That's something I understand. But I told the date, May 8th. So I would say don't book May 8th. Is that?
I mean, like, because I want to go somewhere and never come back. No. You don't have to. Like,
You're graduating. That's
I'm
true.
not graduating. I'm a junior.
So why don't you come back?
Well, I will come back like end of August.
I see. There is reunions. There's all that stuff happening in June. You're aware. May or June. What is reunions? May. Yeah, I would recommend you stick around. You're an undergrad?
I'm an undergrad, yes.
Why won't you stick around for the reunions and all that parties? I would strongly recommend you do that. I go there, you know, of course you do. Yeah.
Undergrads don't have housing for unions unless they're working.
Yeah.
Oh. Somehow all my undergrads always went there. I don't know how it
I
happened.
did it 2 years ago.
Oh, they changed it?
No, I did. I got picked up plastic cups.
You can work there in the bars or whatever, and then you probably get housing.
Yeah.
Yeah.
But it's like selective. It's hard to get.
Yeah, I guess the athletes have it, they have a mafia there that all their friends are them. That's true. Too bad all this is recorded. Okay. How about I make up my mind by Thursday and then send you a notice on Thursday? Is there anyone else? I mean, if I do it May 8th, it's scheduling. This is by scheduling. Is that a problem for anyone? May 8th? That's my tendency, honestly. I mean, my tendency is that you will, to help you by enforcing the stricter requirement and making it kind of, it looks harder. It's not really harder, but that's my tendency, is to go all the way and make sure that you get the maximum out of this class, even if you don't think that this way immediately, but you will. You will thank me, just as all the other undergrads, including your advisor and so on, thank me. So, okay, that's my tendency. Today, we're going to continue discussing on reinforcement learning. We started talking about dynamical systems on Thursday. Oh, one more, sorry, before I forget, one more administrative issue. So that is on Thursday, this Thursday, day after tomorrow, I won't be teaching. Class still in session, so I asked the TAs, Gon and Anand and Rohit, to give you a bit of a survey, help. They will solve questions that we had in homeworks, any questions you want. So, yeah, Gon is here. Any questions you want, you'll be able to, on the fly, please solve this for us. And then he will be able to, he or the colleagues will be able to solve it and go over material with you in class.
We'll try.
They'll try their best. They better. Yeah, Bogdan?
My 6 is like mirror submission to mine. So maybe like my ace is like close.
You don't need to prepare for the exam.
Yes, yeah, this when it issues the next day. All over rush 6.
Doesn't sound like such a strong argument. I mean, actually, you'll be so happy after the deadline. Any other point? Yeah, Carol? I see you guys are all stressed. Same as homework, same as homework. Same, less difficult because homework you have more time to do it at home, but same flavor of theoretical questions. The other thing I will allow is in 3 weeks or so, people that want to submit a project proposal, you're welcome to do that. So 1 page, no more. Give me a project proposal that has a theoretical component. Most of it should be theoretical, if not all. And it can be along the lines of any of the theory that we're studying in this course. And then we'll consider it in the staff and either approve or not approve. I don't expect there to be many of these, maybe a handful. That's what I would expect. Yep.
Are there going to be practice tests posted?
You guys have the wrong mindset, okay? No practice tests, no preparation is needed. The preparation is to come here and sit in class and listen to what I'm saying and then do the homework. That's the only preparation you need. Don't need nothing more than that.
And if we want to do a project, are you going to post some past projects in previous years?
No, I don't think so. Yeah.
I have a question. Another class was going to do a project analyzing the efficiency of an algorithm.
Yeah.
Could I do the same algorithm, but like in one case I'm analyzing efficiency, in this case I'm maybe presenting an algorithm?
The same project as in another class.
No,
What do you get out of it? You will not get out of it. Nothing. I want you to get something out of the class. That's my goal. That's your goal too.
Like one I develop the algorithm, other one I talk about the algorithm I develop.
Same algorithm, do it once. You're not going to do it twice. One algorithm per project, okay. I do see you guys are stressed. But you know what? It just reinforces my belief that you need to see. Look, this is how I was stressed also when it's not like that far away that I was a student. Sure, maybe I'm WH, but I remember when I was a student and I was an undergrad and I was stressed and I studied for exams and so on. But then I also remember, towards like second, third year, I would go to the exam, I would enjoy it. I would enjoy the exam. It was fun for me. Oh, what an interesting question. I would think to myself in the middle of the exam, that's where I want you to be. So once you remove the fact that you're stressed, there's really no reason to be stressed. Whatever you know, and that will be your ability, and you will write down the answer to the question. Once you take that out, it can be a very enjoyable experience. I hope you will see that. Any other questions? Okay, so reinforcement learning. We talked about dynamical systems. Which we formulated as having a state that evolves in discrete time according to an equation. So x is the state, f is the dynamics, xt is the state at time t, the preceding state, and u is the input or control, and w is the noise. And we gave some examples for these dynamical systems coming from physics or coming from natural phenomena, or even LLM, or neural networks for the brain. That's also a dynamical system. We could have a partial observation, which we denoted by y, so yt was the observation. For this lecture, we're going to focus on fully observed case. Partial observation, of course, is crucial and very important. But it's enough to focus on full observation for this lecture, which means that we can see and know x at any given point in time. Furthermore, let me remove the noise for now, so noise is going to be 0 for this lecture, and then we can consider a dynamical system. What we discussed last lecture, last 2 lectures perhaps, is that questions, natural questions with solving a dynamical system. They mean, can we, given a dynamical system, even if it is known, for example, like give you the exact polynomial form of it, it could be NP hard to decide even if this dynamical system is stabilizable or controllable or not. Even that's an NP hard question. Known dynamical system, known state, everything known, decide whether it can stabilize it or not. We proved in class that this is NP hard. You all remember, right? So that seems to be a very kind of depressing conclusion to a subject we just started studying. We want to control an unknown and partially observed dynamical system. We can't even know if a given one is stabilizable or not. Well, that's our starting point. And then we said, okay, how about we take this kind of option 1 of dealing with the difficulty is linearizing. Just like we did for learning without state, prediction from expert advice, online learning, online convex optimization. One technique was to linearize. Lian, you missed the most interesting part. We talked about an exam. They can fill you up later. So the question is now, can we take a dynamical system and perform the same trick, linearization, and compromise computational efficiency or statistical efficiency, at least for some kind of tractability in the lifted space, and that is what we call reinforcement learning. So we started off by talking about Markov chains. That are governed by the equation pt plus 1 is pt times p, where this is the transition matrix. And the object of study in Markov chain is a stationary distribution. When does it exist? When is it unique? That's the subject of ergodic theory. I'm not going to spend any more time on that, but unless there are questions, I could spend more time on that, but that's not the main point I want to reach. Perhaps there are courses about ergodic theory in math department. That's my guess. Are there? Really? There must be something, yeah? So then they study uniqueness and existence of a stationary distribution under and mixing time. It's all sorts of objects like that that are fairly interesting mathematically. There's going to be homework exercise proving the ergodic theorem, so that it's not a hard theorem to prove. It's a very elegant theorem. So every non-stationary, irreducible, and so one condition is irreducibility, and the other is aperiodicity. That's right. So both of these conditions imply a unique and exist of a stationary distribution, and it's possible to prove that. It's not necessary, but it's a sufficient condition. And proving that is a very nice theorem in math that is a guided homework exercise. So I could have taken a dynamical system, converted it to a Markov chain if there is no input, and then try to think about whether a stationary distribution exists, and that is perhaps of interest. Of course, the representation here is going to be inefficient because I'm going to have a distribution over many, many states, and there could be a multitude of them, depending on how fine I discretize the original state. The next object, I want to get to the situation where I can model control of dynamical systems, which is called decision-making or reinforcement learning. So the next object I'm going to add is rewards. That's going to be called the Markov reward process. So Markov reward process not only deals with distributions over states, but also with rewards. So let R of S, which I'm going to note R of S, is called reward at state S belonging to big S. So now usually we don't denote states by the letter X anymore, but I'm going to use the RL convention where we use the letter S. So that is a number. We can assume maybe it belongs to 0, 1. And what is the Markov reward process? So it's governed by the following objects. We have a reward function, we have a state space, we have a transition matrix, and we have a discount factor. So distribution at time t plus 1 is p dt, just like before. But we also have a reward. So let RT is going to be reward at time t. And now the question is, we can ask, so what is the interesting question here? For example, give me an interesting question you can ask about this model. Sorry?
How do I maximize reward?
Right. But notice there is no action here. There's no action. There's no action. So I'm going to add that next, but here there is no action anymore. So, but what can I do? Yeah, Kara? Okay, great. What is the steady state reward, maybe? Okay. So I can ask, for example, question. So starting from S1, what's long-term reward? Yeah?
So I just want to make sure I understand. The rewards are being realized on the observed state, not the probability distribution of the state. Of course, you can
Correct.
analyze what's the expected reward.
Correct.
but that might be different.
That is correct. So every time I reach a state, you can think of like, you know, I had this graph of a certain MVP, let's say this one. So states 1, 2, 3. And I can put probabilities here, 0.3 and so on, 0.7, ta, 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 ta. And I can also put rewards. So my reward here is 1, 2, 3. Maybe these are the rewards. And you can ask now, if I start from 2, what's my expected reward? So in one step, you can calculate it. It's whatever, 0.3 times 1 plus 0.7 times 3. But I can ask what's the long-term horizon reward. And now that depends on whether I have a discount which is strictly smaller than 1 or not. Let's say this discount factor is 1. There is no discount. Then what's the expected long-term horizon reward? That's a good question, actually. So suppose gamma is 1. what do I expect 1 over t summation t rt to approach? So this is what I mean mathematically. I can look at the reward, the next step, the next step, the next step. And this hovers around all over the place. Every time I get around a variable which is the reward. And now I can ask, what's my expected long-term horizon reward? So what do you think that is? Yep.
Oh, I was going to ask a question and then I can answer it.
No, you can just ask, that's fine. Yeah.
So just to make sure for the reward function, right? Like when you're in the same state at 2 different times, it's the same reward, right?
Correct. There are stationary rewards. The rewards are stationary. Every time you're at a certain state, same reward.
Okay, so there's no accessory changing it up for us.
No, this is a stochastic model. Yeah. There is no, that's a good question. So in this model, even in Markov chain, there is nothing adversarial there. Right? It's all stochastic. Yeah. Yeah. Edward?
No, no,
Angelos?
Yeah, I mean, a stationary distribution dot product with the reward.
Very good. Does everyone see that? So this is going to approach, this is going to be equal to pi star in a product with R. So, or if you will, summation over all states, probability of being in that state times reward in that state. So when you take, assuming that there is a stationary distribution, then so I'm now assuming from now on till the rest of the course, all Markov chains are algolic. Okay? So the Markov chains are, I'm going to assume ergodicity. Always, for the rest of the course. If it's always the case, by the way, this is always the case. If you have a graph that's non-ergodic, it describes non-ergodic Markov chain, you can add some small probability of staying in place, it becomes ergodic. The aperiodicity disappears, and it doesn't necessarily mean it's irreducible, but you can make that happen too. I'm going to assume that this is the case. Question, Angelos?
Ergodicity means aperiodic and irreducible. That's what it means.
Yeah. It's not if and only if. So aperiodicity and irreducibility imply ergodicity, imply there is a stationary distribution. There are some Markov chains that don't satisfy these conditions, they're still ergodic. That's interest to corner cases in mathematics from my perspective. Okay, so I'm going to assume that there is a stationary distribution. And it's a unique one. More questions? Does everyone see why this average reward approaches what I wrote here? I'm summing up overall states. What's the probability, after I run it a very, very long time, what's the probability of being in that state times the reward I get in that state? Yeah? Makes sense? Okay. Yeah?
This is maybe a naive question because I haven't seen these ergodic graphs before, but is there some notion of how quickly a graph converges to a stationary distribution?
Yeah. Well, I was just about going to say that it doesn't matter to us, but since you asked, I'm going to tell you. So there is a definition, it's called the mixing time. Of a Markov chain. And this is defined to be T epsilon such that starting from any S, we have that Pt minus P star L1 distance less than epsilon. Okay, so notice that Pt, this is a deterministic quantity, it's not a randomized quantity. Okay, this is equal to P1. P1 is just 1 over S, and the rest are all 0, times P to the T. Okay, so this is defined to be the mixing time. And did people see this before? There must be some math students over here, juniors or something. Yeah, you've seen it? So let's say I really didn't mean to get into it, but it's kind of an interesting subject. So let's say that you have an undirected graph, a random walk over an undirected graph. Okay, this. It so happens that the mixing time is always bounded by a polynomial of the number of vertices. Did anyone see this before? Yeah? Eli, you saw this? Okay. And what's the bound? Can you remember?
N cubed, I believe.
Correct. So it so happens if you have a graph over n cubed vertices, over n vertices, then this behaves like the T epsilon behaves like n cubed over epsilon, something like that. Or maybe log 1 over epsilon, I'm not sure. So this graph defines a random walk. What do I mean by that? It's undirected, unweighted, undirected. So at every node, I take one of the outgoing edges with equal probability. And I repeat it again and again and again. Now, if I have a directed random walk, I should also say the following. So this graph is very nice and simple. The random walk is going to converge here very rapidly. What's the worst case example? Do you know that, Eli? What's the worst case example?
Undirected?
Sorry?
So,
Undirected.
I don't know the directed. Yeah.
Okay. Anyone remember?
Would it be like just one long chain?
Okay, so that's a good guess. So one long chain. And then what will happen is what's the probability from here kind of reach all the way to the other end, and every time it so happens that this behaves, I believe, like something like n squared for this chain. You can analyze it. But the worst case happens for something called, this is really unrelated to the topic of this course. I just remember it. It's something called the lollipop graph. So you have like this. Like there is a click here, click, and another click here, and there is a single kind of edge between them. And then what will happen is a click mixes in one iteration because you can move to any other vertex immediately, and then you're mixed. That's it. The probability with any vertex is the same. But then you have this kind of, I don't remember if there's a chain or a line here, the probability you're going to cross this is very slow, very small. And you need to kind of be equal probability everywhere. So this is the worst case. Now, not someone who has seen this before, but someone who didn't, can you think of an example where directed random walk, so if I have a directed graph, let's say like this, what's the worst case example of a mixing time and what would it be? Just give me some kind of like a bad example. Yeah?
We could try and copy that and just do two edges pointing in opposite.
Yeah, so it's at least n squared, n cubed, that's correct. A claim can be much worse. You had kind of a good guess. Any? So here is kind of a bad example. Let's say that I give you, we've seen this graph before actually in this course. Let's say I have a directed graph that goes like this. It's a chain. And then at every node, there is another edge going back to the first one. Okay? Now, how is the random walk defined on this graph? Every outgoing edge is with equal probability chosen. Okay? You start here. What's the probability you're going to reach all the way to the end? Yeah, Ben? Correct. You see, you must be lucky in every single step of the way to reach. So the probability to reach here is 2 to the minus n. And the mixing time is indeed exponential in n. So that's kind of a big discrepancy between directed and undirected random walks. Okay? Yeah?
Wait, so when we talk about mixing time, like P1, is that defined to be the vector that's 1, where S is n0 everywhere else?
Correct. Correct. Actually, it's true for any starting distribution. Yeah, and it's the worst case, like maximum over all starting distributions that you were going to mix to the stationary. That's how it's defined. So I could have made it max over all P1 in the simplex of S of this thing. That's how it's defined, okay? Any other questions?
But they're equivalent.
What is equivalent?
But because like picking the last will push you to one of them.
Yeah, to one of them, but not necessarily the first. I mean, there is some verdicts, yeah, that's right, for which it's the worst case. Yeah. Okay, so yeah, done with the random walks, Markov chains, okay? I hope we're done with it. That's kind of not, I was just about to say that I only care about gamma less than 1, strictly less than 1. It somehow simplifies what we're discussing and makes things much, much more easier to discuss mathematically. I don't have to take this limit. I mean, who even says it exists, right? It's an infinite sum of things. You can show it does, it's an average, so it does, it's bound between 0 and 1. Nevertheless, there are all sorts of harder situations. So, my question is now, I can define the reward or let me find the question I'm interested in. Question. What will summation t from 1 to infinity, from 0 to infinity, I have gamma to the t. Let's take 1. Gamma to the t minus 1, RT. So that's my question now. What will this go to? Yeah.
Sorry, I don't mean to be pedantic, but just to be sure, is the reason we're not so concerned about mixing times because of this question, or is it because we're assuming that we have finite mixing times?
It's because I have a discount factor. So because I have a discount factor, basically the solution is not going to be at infinity. At some point, you don't care what happens after something like 1 over gamma log 1 over epsilon, everything is epsilon, right? So it diminishes after some time. Basically, the effective mixing time of this chain, doesn't matter what you started off with, is 1 over gamma. It's never more than 1 over gamma. So it kind of forces a mixing time on you, and that's why this is more of a graph structure kind of graph theoretic notion, and there are many interesting, it depends on the structure of the graph, and there are interesting connections to the eigenvalues of the adjacency matrix and so forth. It's very beautiful mathematically. I really do like it, but it's not so much relevant for reinforcement learning. Just in reality, we do have a discount factor. That's the case always. So now that's my question, okay? I start from 1 to infinity, and I want to look at my reward and what happens when I take many, many steps. So what's going to happen here? So I would say it's less easy to kind of understand what happens here. Do you see that? Yeah?
Doesn't it depend kind of on gamma and the mixing time?
Definitely depends. Definitely depends. Yeah, absolutely.
Because if gamma is really small, it's just going to be whatever the first
Correct.
couple of rewards were.
100% agree. So the conclusion from what you said is it depends on gamma, and it also means it depends on where you started off with, right?
Yeah.
So this is a very different question qualitatively than the previous one I asked, which disappeared for me. Oh, over there. Over there, it didn't really depend on where I started off with. At the end, I'm going to mix uniform to some kind of distribution, stationary distribution, and what's going to happen is steady-state behavior. Some limiting behavior. Here, there is no longer a limiting behavior because, as Eli said, the gamma can be very small, in which case, maybe it's zero, I guess. So the one step, you want to get one reward once. Of course, it matters where you start off with. That's the only reward you're ever going to get. Okay? So then, from these elementary considerations, this depends on S1. You agree? If it depends, this is a qualitative consideration. It's not a quantitative consideration. It's qualitatively. We reach that conclusion. And this motivates something very fundamental in the theory of reinforcement learning, theory of all of computer science. That's called the Bellman equation. Okay? So this motivates something very important. So let me define the value function. V of S, I define this to be summation t from 1 to infinity from, RT, gamma to the t minus 1, given that I start, so expectation, so this is, I need to take expectation, these are all random variables, everywhere. Maybe over there it doesn't really matter, it happens with probability 1. Over here, I do need an expectation. So I define this value function to be the infinite horizon reward with a discount factor gamma when I start from a certain state S. This is a function, V is a function from states to the real number. And now the question is, how can I compute this value function for every state of the game that I start off with? You see what my logic here, the reasoning I went through this way, okay? So this it comes very naturally. There is no longer a solution, infinite horizon solution. I need to talk about finite sort of discount factor, and now it changes from state to state. And now I have to talk about a vector solution, not a scalar solution. And how on earth can I compute it? That's my question. Any ideas? Yes, Ben.
You condition on what happens first. Like, do like a first step analysis of what happens.
Okay, very good. Very good. So what we're suggesting, let's open it up one step at a time and see what happens. This is called dynamic programming, okay, or the Bellman equation. So let me write what happens. So this is something you study in Algorithms 101, but I don't think you have seen it motivated from this perspective. And the idea is, okay, this has a recursive structure to it. This V of S has a recursive structure. What is V of S? V of S is equal to what I get at S, reward at S. So that multiplied by gamma to the 0, which is 1. And then I have plus gamma times summation over all states I can move to. Probability I move from S to S prime times V of S prime. Okay, because that's the infinite horizon reward after I move one step. Do you see what I wrote here? It's really a one-step derivation of the value function. I didn't really do anything very deep here. So this is a recursive equation. Notice it's not exactly the same because I have a gamma multiplication here, right? So this is multiplied, so it doesn't mean that it's not an infinite recursion. If I had gamma equal 1, it's somehow an infinite recursion. But with gamma smaller than 1, this is smaller than what I started off with. It does end. After I open it again and again and again, it will end. Okay? So if I write it in vector form, so let V be in 0, 1 to the S, be value function. Then I have V equal R plus gamma P times V. This is what happens in vector form. Yeah? Shirley, why are you so far away?
My computer is dead, so I need to charge it more.
Okay, any questions? Yeah?
Why is B 0, 1?
I assumed that all the rewards it's actually are in 0, 1, but you're right, it's in 0, 1, 0 to the 1 over gamma. Where did I write it? So let's just say real numbers. So I assume the instantaneous rewards, it's a good question by Edward. What is an upper bound on the reward? Yeah?
1 over 1 minus gamma.
Correct. 1 over 1 minus gamma. Because what happens, you can earn at most 1 every duration, and if you sum up all the way to infinity, you have gamma plus 1 plus gamma squared, blah, blah, blah. So this is the Gauss series. That will, the solution to it, the sum of everything is 1 over 1 minus gamma. So it's 0. If you want, you can be very precise. It's 0 to this number, but let's just say real numbers. So, good. So I got this equation. This is called the Bellman equation, and it allows me to solve for V, right? You see that it allows me to solve for V? I have a system of linear equations, and I can write it in vector form. So V times identity minus gamma P equals R. So V is R times the inverse of this thing. So system of linear equations that I can solve in cubic time by Gaussian elimination and get the solution to the Bellman equation. So if I solve, I will know exactly how much reward I get from every starting step that I take. Yeah, Joshua?
Why is the matrix invertible?
Very good question. Does anyone see? There is an answer to that. Does anyone see? Yeah?
Because P is a stochastic matrix and there's identity.
Correct. So identity is between 0 and 1, all the eigenvalues, right? Now P is a stochastic, not double stochastic, depending on. So the eigenvalues are between also 0 and 1, I guess minus 1 and 1, minus 1 and 1. And I multiply it by gamma. So gamma is strictly smaller than 1. And for that reason, you can show that it's invertible. I actually don't need invertibility. I'm going to erase this because there are some edge cases if there is no stationary distribution and so on. There are all sorts of problems that can arise. I don't need a stationary distribution when I go to the finite discount factor, strictly less than 1. I actually don't need ergodicity. Everything is still well defined without ergodicity. There is no infinite limit, nothing of the sort. So I have a system of linear equations that I can just solve. So as long as it's non-degenerate, I guess, or even degenerate, there are many solutions. There could be many solutions, but there is definitely at least one, as long as it's not over-constrained. Yeah. And it's not over-constrained. The dimension here is exactly S. Make sense? So there's always at least one solution. But there could be more. In that sense, it doesn't have to be invertible. I don't require here ergodicity. Once I move to the gamma less than 1, I don't require ergodicity anymore. That was a very good question. Any more questions? Good. So, okay, I said what I wanted to say about rewards. So I have now a Markov chain with rewards. But what I really want to get to is making decisions and the control problem and reinforcement learning. So I need to introduce what does making decisions look like. And here we get to the additional model of Markov decision process, where I add an additional component, not only reward, state, transition, and discount factor, I also add an action set. this will correspond to U in control. So it's kind of unfortunate to use different notations, but I will use the notation that is common for each literature. So we now have same Markov chain, we only had P. That's it, we only had P, nothing else. And S, I guess, over P. Now we have rewards, we added the rewards and the discount factor, and I'm now adding an additional component, which is to make an action set. So for every state, I can take A in action set by taking an action that will affect my future state. So these transitions are now P, S, S prime, A. This is the probability of moving from S to S prime, given that I take action A. And similarly, I can have the reward can be S, S prime A. Let me just do R S of A, do RSA. So this is the reward taking A at S. So suppose I always take action 1. That's what I do. Always action 1. Doesn't matter where I am, take action 1. Then what do I have? Yep.
Then you just have the whole.
Correct. Then I have Markov reward process, right? So I have a transition from state to the next state. It's a probabilistic transition. I have the rewards. It's just the R with A being 1. And it's a Markov reward process. And I can compute the value function of it, which is kind of the infinite horizon discounted reward. But now I can ask a more sophisticated question, not just what my reward is going to be, but how can I maximize my reward? So that's the question. How to maximize rewards. So I'm looking for a mapping from state to action that will maximize my infinite long-term horizon reward. That's what I'm looking for. This kind of a solution is called the policy, because it's a mapping from state to action. Now, it's clear to you by just the very definitions that I gave you that an action, you always should take the same action at every state. It doesn't make sense that to take a different action in the same state. If there is one action that's more beneficial, why would you ever change it to something else if you're in the same exact situation? The history doesn't matter. This is a Markovian model. Okay? So that's an important point. So a solution concept is called the policy. Usually denoted by pi. So pi is a mapping from state to action. It can be randomized or deterministic. And the reinforcement learning question is, that we will answer today, I think, yes we will. So how do we find pi to maximize summation t from 0 to infinity, gamma to the t, rt plus 1. Given that we always play action t according to pi st. So we play according to the policy. This means that I choose action according to what the policy says at state st. And you can even ask a more basic question, is there such a solution? Does it always exist? Is it unique? And so forth. Yeah.
Is there any reason that we're starting at t equals 0 instead of t equals 1?
No, we can do 1. I don't know. I mean, it's the same, right? I did t plus 1.
Yeah.
You prefer 1? I can do 1.
Oh, I didn't realize.
It's the same thing, yeah. I just changed the index. Any questions? So let me write a theorem. So for any MDP, there exists a pi star which is optimal, meaning it attains the maximum value you can obtain here. So far I didn't say anything, of course there is, but it's deterministic. So that's already less trivial because deterministic is not clear why there would be a deterministic policy that is optimized, has the best possible value. And it can be found in time O of S times A over epsilon squared, let's say. Okay, so pretty efficient in the representation of the problem. So by that I mean epsilon close to optimality in this time, this much time. Yep.
I agree that we need to prove it. Didn't you say just now that it should be obvious that it should be deterministic?
No, I said it's not obvious. It's not obvious.
But I mean, before that, you were saying, you know, if I'm at a given state, it doesn't make sense to take any other action than the one which, you know, corresponds to the best policy.
But it could be distribution of actions. Maybe there are two actions that are the same. Or several of them. So actually the case is that you could have a randomized policy that is optimal. There exists. I'm not saying that there aren't. I'm just saying that there is always a deterministic one. Okay? It's not an obvious statement, I think. Is it clear what I said? So there could be randomized, that are optimal, but there is always a deterministic one. Yeah?
I'm just thinking back to like the case of the two-vector distribution where, you know, sometimes we can construct all those like sequence of losses such that choosing one determines something always doesn't perform in all sections.
Yeah.
So, is there not such a case in this case?
That model is an adversarial model. The losses are adversarial. And they depend on what you did in the past, and can depend on what you did in the past and what you choose, this iteration and so on. This is a stochastic model inherently. So everything is fixed a priori. And from that point on, there is no more noises or anything. The transition captures the noise already. Yep. Yep.
Because our reward here is not adversarial.
It can, well, the rules of the game, I should say what the rules of the game are. The rewards are chosen before you start playing. They can be chosen adversarially, but before you start playing. Now you start playing from time 1 to infinity, and they cannot change anymore in the middle. In the experts, prediction from expert advice, online learning, I make a decision, then it gives me a reward. Then I make another decision, then it gives me another reward. It can be completely adversarial. And changes. This doesn't change, it's fixed. Make sense? Okay. So how can we find the optimal policy? Yeah?
Is like a value iteration.
Sure, but I didn't say what it means. But let's start with some kind of more basic arguments on how to find it. I wanna have the same kind of argumentation that we did for a Markov reward policy, remember that we wrote this value function, right? So, very similarly, let me write the Bellman equation for an MDP. So Bellman equation for MDP. So suppose I play according to a fixed pi, which maps from S to A. So this means that the action I take at time t is pi of st, or distributed according to pi of st. How can I write the Bellman equations for this situation? What do I have at this point? I have a Markov reward process. I don't have any more free choice at that point because I'm restricting myself. I always choose action according to this policy, always. So there's no more free choice, right, at that point. Suppose that's what I do. So my claim is if I play according to pi, I have a value function which I call v pi, which is a mapping from S to the real numbers. So that is v pi of S, the summation over t, gamma to the t, r to the t plus 1, given that at is pi of st. Expectation. Is the definition clear? If I play according to a certain policy, always do 1, always do 2, or whatever, some kind of, any policy, doesn't matter which one. Then I can define a value starting from a certain state, and all the considerations I said about Markov reward processes are still valid. Yeah, Jerry?
So if we think of it this way, is this not just kind of like the previous one, but you just change your p, like each row is like the new, like p or whatever, and then you can solve it.
Exactly right. Exactly right. So I can write v pi by the same v pi of s is equal to exactly the same what I have there. So this is going to be r of s and a t. So a t chosen according to the pi at s plus gamma. Then I have summation over s prime b s s prime a. So that's the probability I move from s prime to s. From S to S prime, given that I take action A, and this is also times V pi of S prime, and then this is given that A is pi of ST. Okay? So, I can change. Since I always play A from pi of st, this is what Jerry was saying, I don't actually need to sum up over all possible A's and condition on them and all that. I can just say, now I'm playing policy pi. That's it. This is p pi. There is a p pi here that governs how I switch from S to S prime. And similarly, I don't even need to say this A here in the reward. I can just call it R pi. So for every state, there is an expected reward that I'm going to get. So I get this kind of equation. And this can be solved in the same way. This is a system of linear equations we can solve. And by solving it, I get the value of a policy. Meaning for every starting state, what's the value I get starting from that state until infinitum, taking the same action for that policy. However, this doesn't necessarily give me a way to solve for the best policy. Okay, for every policy this is true. But how do I solve for the best policy? So there is something extra that the optimal policy satisfies, and this is called the Bellman optimality. Equation. So let pi star be the optimal policy. What kind of equation can I write for pi star? Yeah, Alex?
Well, would you do the same, but then on the right you do max over like all the actions?
Very good. So V, let's call it V star. V star of S, it satisfies this for the pi star. But because it's optimal, it means I cannot improve reward at any state. There is no better action I can take. If there was a better action, I would take it. It would be more optimal. So I can't. So this means it's bigger or equal to, or if you want, equal to, maximum over all actions. And here I can take R of SA plus gamma summation over S prime and A, P S S prime A, V star of S prime. Okay. So for every action I could take, I'm bigger than this kind of reward that I will obtain, taking this A and then continuing playing with the optimal policy. Questions? Yeah?
This works because the V star is this, which is conditioned on that action that you choose, right?
V star is a mapping from state to action, right? And it takes the best action, it's the optimal that maximizes all possible rewards. And I'm saying the value of this, so V star is the value of that policy starting from any state S.
Oh, sorry, I meant V star S prime.
Yeah, and this is V star S prime. I mean, it means I continue to play optimally from this point on. Still, it must be the case that I'm taking the best action that max. So this is just recursing, right? If I didn't have max A, this is true for any policy. Now, I'm saying that for this optimal policy, it must be the best action instantaneously. Otherwise, I could improve it. Just equal to the best possible action I can take, and then continuing optimally from there. Recursively. I mean, did I understand your question? I'm not sure.
I guess what I'm worried of, and I'm not sure how this avoids this, is you take this, you take a path that in the short term looks like it's better than its neighbors, but then you end up somewhere like much worse in the long run than if you had taken.
Okay, I understand your question. So you're saying, why can't I not take something that looks suboptimal now, but then it becomes optimal later on? Who can answer this question? Yeah, Joshua?
It's because the value function already takes into account the total future rewards.
Exactly. Right. So it's not like it's not a local, V star already takes infinite horizon into account. Okay? So once I reach the next state, I'm playing optimally. Then why would I take something that includes that already is not optimal right now? This is dynamic programming, right? It's exactly dynamic programming that you build it backwards. Okay? This is a very important question. I don't know if I answered it sufficiently well or not. I just need to reason about this for a minute. Make sense to everyone? Yeah?
My question is, I guess V star we don't know that at any point, right?
Right.
You can't really say anything about it.
Yeah, we have no clue what V star is. But can I solve this? That's my next question. Yeah?
I guess it depends on the action space, right?
Let's say it's discrete. discrete state, yeah, I should have said. For this class, okay, all chains are ergodic, gamma is less than 1, S and A are finite. Okay. It's actually not, all of these things are easy to cancel out. So suppose it's finite.
In that case, then this track can also just roll out, all possible rollouts with states match.
Correct, correct. And how will it look like? I agree.
You have a big table of mass and headache.
Which is called?
Key table.
No, I didn't define Q function on purpose. In my opinion, it only confuses me, the Q function. But if I have a system, so it's an inequality, right? So this can be replaced by an inequality. Bigger or equal, I think this is what you said. It's bigger, this thing is bigger or equal to than RSA plus ta 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 for every A. So I have a linear inequality for every A. And this is called linear program, right? I have a linear program, which we already have seen in this class, and we even showed how to solve. Okay? So this is a linear program. It's slightly more complicated than, so before we had a system of linear equations. Somehow no one complained because I had equalities. Now I have inequalities. It's not equalities. But I just have a finite, like 10 or whatever, how many actions I have for every state. And I have S many variables. And how many inequalities? So I have S variables. How many inequalities? SA, right? SA. So for every state, I have A. So SA inequalities. And maybe I want to say here, maximize summation over S pi V star of S. You don't even need that. You don't even need an objective function, but if you want, you can maximize the sum. And this is solvable in polynomial time. And not only that, the solution to a linear program is always obtained at a vertex. Everything is linear, so that's why it's deterministic. A vertex theory corresponds to a deterministic policy. And that also shows you can solve it in polynomial time. Yeah, Kara?
Sorry, I didn't understand what the inequalities were.
Oh, max I can replace by this. So if I know that the V star of X is equal to the maximum over A of something, then I know it's bigger than any something for every A I replace. Okay? Yeah. Yeah?
It seems like because we just want feasibility, maybe we can just maximize the constant as the objective.
Yeah, you can maximize nothing. Maximize 0. That's also fine, maximize, it doesn't really matter. It's a feasibility in a program. You can put it in a direction if you want, but you don't have to. So this is an even easier linear program than with an objective function. Yeah? Okay, but maybe linear programming is, as I said, kind of, heavy, and you need to reason about inequalities, equalities, and polyhedra, and, simplex, whatever, algorithm, and all this more complicated stuff. So I do want to show you a simple elementary algorithm and its analysis to solve in reinforcement learning, okay? I have like 10 minutes. It's exactly sufficient. Okay, so as someone said, this is called value iteration. Algorithm. And the idea, so all ideas in RL come from the Bellman equation. The idea is to take this Bellman equation and iterate over it. So maybe you don't know the V star, but you plug in some random values over there, and you want them to become closer and closer to the true values. And how are you going to do it? Well, just take the maximum and plug that back in. And think of an iterative process. So let me write it down. So you start with Vs, V1 of S to be 0 for all S. And then for T, equals 1, 2, and so on, you do the following. You take Vt plus 1 of S to be the maximum over A, RSA plus gamma, summation over S prime, PSS prime A, Vt of S prime. That's the algorithm, okay? So just, you don't know the V star, start with 0, keep on doing the max, iter, and that's it. Then you return it after some big number, you return whatever you get. And how do you get the policy from that? Yeah, Jerry?
Just argmax.
Argmax, yeah. So V gives you value function. Then you can take the action at every state that maximizes the infinite horizon reward according to this equation. Okay. Questions about the algorithm? It's a very simple algorithm, right? Very easy. Okay. Then so let RT of S be ST plus 1. So VST plus 1 of S minus VT of S. So that's kind of how much close, sorry, let's do it. Let's take V star of S minus VT of S. So how close am I to the optimum? Question? And the theorem maybe I do need. Okay. Theorem is that the infinity norm of RT plus 1, so this means the maximum entry of RT plus 1 is at most gamma to the T are 1. So this is a very strong theorem. It says you start off with some kind of distance from optimality, you will converge exponentially fast. So after logarithmically many iterations, you basically recovered the optimal value function. Okay? Very fast convergence. Okay? Any questions about what the theorem says or what the algorithm is? It's a very intuitive, very easy algorithm. You can code it up. Very intuitive, very simple theorem. And proof is equally easy. I'll just do it now. Unless there are any questions about the theorem. No? So let's prove. So proof. So at every state we have that Vt plus 1 of S, this is the maximum over A, RSA plus gamma summation S prime, PSS prime A, Vt over. I know that because that's how I defined my algorithm. That's exactly what I defined it to be. So this is bigger than RSA star. A star is what the optimal action, the action that the optimal policy would take in this state. It doesn't have to be the same state as the same action as the optimal policy, but it's at least as good as that for the particular iteration that I take. Is this okay? Yeah? You understand what I wrote it here? So, of course, the optimal policy is better than my policy. But I pick an A. It doesn't have to be the same A as what the optimal policy is picking. He might have another action that it's taking because it has different values. But for the values I have, I'm picking the best one. But on the other hand, I know V star of S is equal to RSA star plus gamma summation S prime P S prime A star V star of S prime. This is by the optimality equation. So let's take the difference between these two things. Difference. So what do I get? I get this minus this is RT plus 1 of S. And that is less than equal to, this is 0, plus gamma summation S prime P S S prime A star RT of S prime. Right? The R disappears. So therefore, I get the following. I get that R T plus 1 of S is less than gamma, what I wrote here, summation S prime, S S prime A star, RT of S prime. Yeah, I just rewrote what I got. So in vector form, I have the following. I have RT plus 1 less than gamma P, I'm going to call it PA star RT. So this is the P that happens when I choose A star at every state, according to the optimal policy. Okay. So this is true for every coordinate, in particular, RT plus 1 infinity less than gamma, and then I have the infinity norm of this thing. And this is less than gamma, because this is a stochastic matrix, RT infinity. Because P, for any A star, this is stochastic matrix. The entries don't sum up to more than 1. So I cannot enlarge my infinity norm, coordinate-wise. Yeah. Okay, so by induction I get this. Very simple proof. Yeah.
In the first line there, why are you putting A into BFT?
S prime, because I had a typo. Okay. Questions? Yeah?
So I guess, does the runtime need also like some log like forgetment or something after?
Yeah, okay, what's the running time? This means that for epsilon approximation, I need log to the base of gamma R1 infinity divided by epsilon iterations. Yeah. So it's very fast. It's an exponentially converging algorithm. And a very simple one, very simple algorithm. So I'm kind of almost over time, but I will take this extra minute over time because I want to conclude RL and say the following. Why are we not using this algorithm in practice? What's the problem here? Very exponential convergence, so simple, so easy to prove. Yep.
You need to discretize everything?
It depends on number of states, right? Number of states, number of actions. Number of states is humongous in practice. In every application, Go, all these things. Or if I start from a physical application, like a car or an airplane, and it's discretized space. Of course it's horrible. So this is completely impractical. Even though it's a beautiful result, it's not really meaningful. What I really want to do is to work in the representation of the actual problem and get an efficient algorithm there. And that's what we're going to do next. So summarize, I went over RL. There's not too much theory. I mean, people in RL know that. That's why they have all sorts of function approximation and other heuristics to try to reduce the number of states. okay? And many times they work. There are many interesting ideas. But in terms of theory, you're already at a disadvantage. This course is about theory. You discretized, you're in trouble. You have exponential many things. So what are you going to do now? You can try to resolve the problem that you created yourself. But I will try to show you an alternate idea, which is not to create that problem to begin with, and work with the original presentation and get more efficient methods. Especially I'm interested in learning in these high-dimensional dynamical systems and decision-making in them. Okay, that's it for today. Thursday, TAs think of questions. They will do problem solving here of previous homeworks, and I'll see you next Tuesday.